Tonight, we are going to shatter a picture that has been stuck in your head since you were a child. You know the picture. A tiny sphere at the center, the nucleus, dense and solid and somehow stable. And around it, tiny electrons in neat orbits, circling like planets around a miniature sun, each one staying dutifully in its lane, following a predictable path at a predictable distance. You have seen this picture on posters, in textbooks, in science museum displays, in the logos of nuclear power companies and physics departments. It is one of the most widely reproduced scientific images in the world, and it is completely, fundamentally, irreversibly wrong. Not wrong in the way that a simplified model is wrong, where the real thing is more complicated but roughly similar. Wrong in every meaningful sense. Electrons do not orbit. They do not have defined paths. They do not stay in their lanes. They do not have positions at all, in any ordinary sense of the word, until the moment you measure them. And the moment you measure them, the act of measurement changes what they are doing so completely that the result tells you where they were when you looked, but nothing about where they will be a moment later. And that is just the electrons. When we get to the nucleus, things get stranger still. The nucleus is held together by a force so powerful that it makes the electromagnetic force that governs all of chemistry look weak in comparison. The energy stored in a nucleus is so concentrated that a single kilogram of it, fully released, would equal the energy output of the most powerful thermonuclear weapons ever built. The forces inside the nucleus operate at ranges so small that they become effectively zero at the diameter of a single proton. They are the strongest forces in nature, and they operate at the smallest scales in nature, in a region smaller than the atom by a factor of 100,000. And the particles inside the nucleus, the protons and neutrons, are themselves not fundamental. They are made of quarks, bound together by particles called gluons, in a dynamic so complex and so far from our everyday intuitions about matter, that physicists spent decades and billions of dollars in particle accelerators just beginning to understand it. And through all of this, through the nucleus and the electrons and the quarks and the gluons and the fields that hold everything together, if you could somehow extract all the actual matter from an atom and leave only the empty space, you would find that the atom is, by volume, approximately 99.99999% nothing. If you removed all the empty space from every atom in every human being on Earth, every one of the 8 billion of us, the matter that remained would fit inside a single sugar cube. Your hand is not solid, your chair is not solid, the floor beneath your feet is not solid. What you experience as solidity, the hardness of surfaces, the resistance of matter to being compressed, is not the result of atoms being packed tightly together. It is the result of invisible quantum forces pushing back against compression. The atoms in your hand and the atoms in the table are almost entirely empty space, separated by quantum mechanical repulsion. This is what the atom actually is, and tonight we are going to understand it properly. Let us begin at the beginning, with the question that started it all. Is there a smallest piece of matter? If you take any object and cut it in half, and cut it in half again, and again, and again, do you eventually reach a piece so small that it cannot be divided further? Or can you always cut it smaller? This question was asked by ancient Greek philosophers, most famously by Democritus, who lived in the 5th century before the Common Era. Democritus argued for the existence of a smallest, indivisible piece of matter. He called it atomos, from the Greek words meaning uncuttable. His atoms were indestructible, indivisible, and moved through empty space to combine in different arrangements, producing all the different objects in the world. This was a remarkable idea, arrived at by pure reasoning with no experimental evidence. Democritus was right in the broad strokes. Matter is made of discrete units. There are smallest building blocks. He was wrong in the details, as we will see. But the intuition was extraordinary. Democritus's idea was rejected by Aristotle, who was one of the most influential philosophers of the ancient world. Aristotle believed that matter was continuous, that you could always divide it further, that there was no smallest piece. Because Aristotle's authority dominated Western thought for nearly 2,000 years, the atomic idea was largely suppressed. It came back in the early 19th century through chemistry. John Dalton, a British chemist, noticed in the early 1800s that chemical compounds always combined in fixed ratios by mass. Water was always 8 parts oxygen to 1 part hydrogen by mass. Carbon dioxide was always 12 parts carbon to 32 parts oxygen. These fixed ratios made no sense if matter were continuous, but they made perfect sense if matter consisted of discrete atoms, each with a fixed mass, combining in fixed numerical ratios. Dalton proposed his atomic theory in 1803. In his model, atoms were tiny, indivisible spheres. Different elements had different-sized atoms. Compounds were formed when atoms of different elements combined in simple numerical ratios. This was essentially Democritus's idea, now supported by chemical evidence. For the next several decades, atomic theory was accepted as a useful framework for chemistry, but the actual existence of atoms remained controversial. Many leading scientists of the late 19th century, including Ernst Mach, believed that atoms were useful fictions, mathematical constructs that helped organize chemical knowledge but did not correspond to real physical objects. The question was settled in 1905 by Albert Einstein in one of the 4 great papers he published in that extraordinary year. Einstein analyzed Brownian motion, the observed jiggling of tiny particles suspended in liquid. He showed that this jiggling was the result of the suspended particles being bombarded by individual molecules, and he derived a precise mathematical formula relating the observable properties of the Brownian motion to the size and mass of the molecules doing the bombarding. The formula allowed the size of atoms to be calculated from the observed motion of visible particles. Experiments confirmed Einstein's predictions precisely. Atoms were real, they had definite sizes, they were not fictions, and their sizes could be inferred from observable phenomena. But by the time atoms were conclusively confirmed as real, physicists had already started discovering that atoms were not what Dalton had imagined. They were not indivisible, they had structure, and the structure was far stranger than anyone had expected. The first crack in the indivisibility of the atom came from electricity. In the 1890s, physicists studying electrical discharge in gases noticed that the electricity seemed to be carried by something that was present in all materials, regardless of what element they were made of. This universal carrier of electricity was identified as a particle, much lighter than any atom, that could be extracted from atoms under the right conditions. It was named the electron, and its discovery was announced by J. Thomson in 1897. The electron was the first subatomic particle. Its existence proved that atoms had parts. They contained electrons, but electrons were negatively charged, and atoms were electrically neutral. So atoms must also contain positive charge, distributed somewhere. Thomson proposed what became known as the plum pudding model. Atoms were like a diffuse cloud of positive charge, with electrons embedded within it like plums in a pudding. The positive charge was smeared throughout the atom, and the electrons sat within it, vibrating but more or less fixed in position. This model seemed reasonable. It explained electrical neutrality. It could be made to predict the spectral lines of hydrogen with some modifications. It was the best available picture of atomic structure in the first decade of the 20th century. Then, in 1909, Ernest Rutherford, working with Hans Geiger and Ernest Marsden at the University of Manchester, performed an experiment that destroyed the plum pudding model completely. Rutherford's experiment fired a beam of alpha particles, which are positively charged particles consisting of 2 protons and 2 neutrons, at a thin sheet of gold foil. If Thomson's plum pudding model were correct, the diffuse positive charge of the gold atoms would exert only gentle forces on the alpha particles, and they would pass through the foil with only slight deflections. Most of them did, but some of them did not. Some alpha particles were deflected by very large angles, and a few, a tiny fraction, bounced almost straight back. Rutherford later said that this was the most incredible event of his scientific life. It was as if you had fired artillery shells at tissue paper and they had bounced back and hit you. A diffuse cloud of charge could not do this. The only way to deflect a fast, heavy, positively charged particle through a large angle was if almost all the positive charge of the atom were concentrated in a tiny, dense region at the center. Rutherford concluded that the atom had a nucleus, a compact, dense, positively charged core, much smaller than the atom itself. His calculations showed that the nucleus was roughly 100,000 times smaller than the atom. If the atom were the size of a football stadium, the nucleus would be the size of a pea at the center of the field. And the electrons were somewhere in the vast empty space surrounding the nucleus. The 99.99999% of the atom that was nothing. This was the Rutherford model, and it immediately raised a devastating problem. In classical physics, a charged particle moving in a circular orbit emits electromagnetic radiation. It loses energy. A classical electron orbiting a nucleus should radiate energy continuously and spiral inward toward the nucleus in a fraction of a second. All atoms should instantly collapse. No stable matter should exist. And yet stable matter exists. Evidently, something was wrong with applying classical physics to electrons and atoms. Niels Bohr, a young Danish physicist working with Rutherford, proposed a solution in 1913. He suggested that electrons and atoms could only occupy certain specific orbits with specific energies, and that while in these orbits, they did not radiate. They could jump from one orbit to another by absorbing or emitting a photon with exactly the energy difference between the orbits. But they stayed in their orbits without radiating as long as they remained in any single orbit. Bohr had no physical justification for this rule. He just imposed it because it worked, and it worked remarkably well. Using his model, Bohr could calculate the spectral lines of hydrogen, the specific wavelengths of light that hydrogen atoms absorbed and emitted, with extraordinary accuracy. The agreement between his predictions and the observed spectra was not approximate. It was exact to the precision of the measurements. But the rule itself was mysterious. Why could electrons only be in certain orbits? What was special about those orbits? The answer came from Louis de Broglie in 1924. De Broglie proposed that electrons, like light, had wave properties. Their wavelength was related to their momentum, and the allowed orbits in Bohr's model were the orbits in which the electron's wave fit perfectly around the nucleus, an integer number of wavelengths fitting exactly into the circumference of the orbit. The electron wave reinforced itself, creating a stable standing wave. The forbidden orbits were the ones where the electron wave would destructively interfere with itself, canceling out. This wave picture made the Bohr orbits comprehensible, but it also pointed towards something even more radical. If electrons were waves, what exactly was waving? What was the physical nature of this electron wave? This question was answered by Erwin Schrödinger and Werner Heisenberg in 1926. Working independently and arriving at mathematically equivalent but physically very different seeming formulations. Their work was the birth of modern quantum mechanics, and it replaced the Bohr model, which was already a radical departure from classical physics, with something far more radical still. In quantum mechanics, the electron does not have a definite position. It does not orbit the nucleus in any classical sense. Instead, it is described by a wave function, a mathematical object that tells you the probability of finding the electron at any given location if you measure its position. The wave function is spread out through space. It does not sit in one place. It is, in a precise mathematical sense, everywhere at once with different probabilities of being found in different places. This is not a statement about our ignorance of where the electron is. In classical physics, you might say that the electron has a definite position, you just do not know what it is. In quantum mechanics, the position is genuinely indefinite, not just unknown, undefined. The electron does not have a position until you measure it. The shapes of these quantum wave functions, called orbitals, are the true picture of where electrons are in atoms. They are nothing like the neat circular orbits of the Bohr model or the solar system model taught in schools. They are three-dimensional probability clouds, some of them spherical, some of them shaped like dumbbells or clover leaves or toruses, some of them pointing in specific directions, some of them spread throughout the entire atom in complex nodal patterns. The lowest energy orbital, where the electron in a hydrogen atom spends most of its time, is a sphere of probability centered on the nucleus. The electron is most likely to be found close to the nucleus, but has a finite probability of being found anywhere, including at very large distances. There is no sharp boundary. The electron cloud fades gradually to near zero probability far from the nucleus, but never quite reaches zero. This probability cloud is the atom, not a solid sphere, not a nucleus with orbiting electrons. A nucleus at the center, and around it, a diffuse, probabilistic, inherently quantum mechanical distribution of electron probability, with no sharp edges, no definite positions, no classical trajectories. And the size of this probability cloud, the rough extent of the region where the electron is likely to be found, is the size of the atom, not 100,000 times the size of the nucleus. exactly 100,000 times the size of the nucleus. The nucleus is so much smaller than the atom that the ratio defies easy visualization. The hydrogen atom is about 1 angstrom across. 1 angstrom is 1/10,000,000th of a meter. The hydrogen nucleus, a single proton, is about 1 femtometer across. 1 femtometer is 1 quadrillionth of a meter. The proton is 100,000 times smaller than the atom. The volume of the proton is 1 quadrillionth of the volume of the atom. Everything else is by volume, empty space. But not empty in the sense of nothing happening. The electron wave function is spread through that space. The electromagnetic field between the electron and the nucleus fills that space. The quantum mechanical interactions that give rise to chemistry, to the formation of molecules, to the properties of materials, all happen in that space. It is empty of matter, but full of fields and forces and quantum probability. And it is this emptiness, this enormous gap between the nucleus and the electron cloud, that makes solid matter seem solid without being solid. When you press your hand against a table, the electron clouds of the atoms in your hand approach the electron clouds of the atoms in the table. As they get close, the quantum mechanical principle called the Pauli exclusion principle, which forbids 2 electrons from occupying the same quantum state, creates a repulsive force. The electron clouds cannot overlap. They push back. Your hand cannot pass through the table, not because atoms are solid, but because quantum mechanics forbids the electron clouds from interpenetrating. Solidity is an emergent phenomenon. It arises from the interaction of quantum mechanical probability clouds, not from any inherent hardness of matter. If quantum mechanics worked differently, if the Pauli exclusion principle did not exist, matter would not be solid. You would pass through walls. Stars would not exist. Chemistry would not exist. The universe would be a cold, structureless soup. The Pauli exclusion principle, formulated by Wolfgang Pauli in 1925, is one of the most consequential facts in physics. It says that no 2 identical fermions, particles with half-integer spin, can occupy the same quantum state simultaneously. Electrons are fermions, so are protons and neutrons. The Pauli exclusion principle applies to all of them, and its consequence is the structure of matter as we know it, the periodic table, the properties of elements, the existence of solid objects, the stability of stars. All of it flows from this single quantum mechanical rule. Now let us go into the nucleus. The nucleus of an atom contains protons, which carry positive electric charge, and neutrons, which carry no charge. In all atoms except hydrogen, the nucleus contains multiple protons, multiple positive charges packed into a region 100,000 times smaller than the atom. The electromagnetic force, which causes like charges to repel, acts between these protons with enormous strength. The protons in a nucleus should be flying apart at tremendous speed. They should not be able to coexist in such a tiny volume. The electromagnetic repulsion should tear any nucleus with more than 1 proton apart instantly. And yet, nuclei with dozens or even hundreds of protons exist. Some of them have been stable for billions of years. What holds them together? The answer is the strong nuclear force, the strongest of the 4 fundamental forces of nature, a force that acts between protons and neutrons, but only at extremely short distances. At ranges larger than about a femtometer, the strong force drops to essentially 0, but inside the nucleus, where protons and neutrons are within that range of each other, the strong force is overwhelmingly more powerful than the electromagnetic force. It is approximately 100 times stronger. It overwhelms the repulsion between protons and holds the nucleus together. The energy stored in the strong nuclear force, holding the nucleus together against the electromagnetic repulsion trying to tear it apart, is the nuclear binding energy. When a nucleus is split in nuclear fission, or when light nuclei fuse together in nuclear fusion, some of this binding energy is released. The energy released per unit mass in nuclear reactions is millions of times greater than the energy released per unit mass in chemical reactions. This is why nuclear weapons are so devastatingly more powerful than conventional explosives, and why fusion power, if it can be controlled, promises essentially unlimited energy. The strong force is not just holding protons and neutrons together in the nucleus. At a deeper level, it is holding together the quarks inside each proton and neutron, and here is where the story of the atom goes to its deepest level. Protons and neutrons are not fundamental particles. They are made of quarks. This was established in the 1960s and 1970s through experiments at particle accelerators that fired electrons at protons with enough energy to probe the internal structure of the proton. The results showed that the proton was not a uniform ball of charge. It had internal structure. It contained discrete, point-like constituents. These were identified as quarks. A proton contains 3 quarks, 2 up quarks and 1 down quark. A neutron contains 3 quarks, 1 up quark and 2 down quarks. The charges of the quarks add up to give the correct charge for each particle. The up quark carries a charge of plus 2/3 of the elementary charge. The down quark carries a charge of minus 1/3. 2 up quarks and 1 down quark give plus 1, the charge of the proton. 1 up quark and 2 down quarks give 0, the charge of the neutron. Quarks are, as far as we know, truly fundamental. They have no internal structure that has been detected. They are point particles. But they are very different from the electrons in a crucial way. Electrons can exist freely, outside of atoms. You can extract an electron from an atom and have a free electron, moving independently through space. Quarks cannot be isolated. You cannot extract a single quark from a proton. You cannot have a free quark. This is called confinement. Quarks are permanently confined inside composite particles called hadrons, of which protons and neutrons are the most common and stable examples. The reason for confinement is the nature of the strong force. The strong force is carried by particles called gluons, and unlike the electromagnetic force, which gets weaker with distance, the strong force between quarks does not weaken as you pull quarks apart. It stays roughly constant. This means that as you try to separate 2 quarks, you have to put in more and more energy, and at some point, the energy you put in is enough to create a new quark-antiquark pair from the vacuum. Instead of separating the quarks, you have created more quarks. You end up with more particles, each still containing quarks, but you never get a lone quark. This is one of the most bizarre features of the strong force. It is as if you tried to separate the north and south poles of a magnet by cutting it in half, and instead of getting a north pole and a south pole, you got 2 complete magnets, each with both poles. Quarks are always paired or tripled, never alone. The gluons that carry the strong force are themselves subject to the strong force. Unlike photons, which carry the electromagnetic force and do not interact with each other, gluons interact with each other. This self-interaction is what makes the strong force so different from electromagnetism, and it is what leads to confinement. Inside a proton, the 3 quarks are connected by a dynamic, constantly fluctuating web of gluons. The gluons are not static. They are being constantly exchanged, emitted, absorbed, creating and annihilating quark-antiquark pairs from the vacuum. The interior of a proton is not 3 quarks sitting quietly. It is a chaotic, dynamic sea of quarks and antiquarks and gluons, constantly interacting, constantly creating and destroying virtual particles. And here is something remarkable. The mass of the 3 quarks inside a proton, if you could somehow weigh them separately, adds up to only about 1% of the mass of the proton. The other 99% of the proton's mass does not come from the quarks. It comes from the energy of the gluons and the kinetic energy of the quarks moving inside the proton. From the dynamics of the strong interaction itself, this is the most dramatic example of Einstein's famous equation in action. Mass is not just mass. Mass is also energy. The proton has the mass it has largely because of the binding energy of the strong force, the kinetic energy of the quarks, and the energy of the gluon field inside it. The matter you are made of is, in large measure, not matter at all. It is energy. It is the binding energy of the strong force, manifested as the mass of protons and neutrons, manifested as the mass of atoms, manifested as the mass of you. You are mostly energy. Your mass comes mostly from the binding energy of quarks inside protons and neutrons. And those protons and neutrons are mostly empty space, filled with a dynamic quantum field. And the atoms they make up are themselves mostly empty space, with a tiny dense nucleus surrounded by a vast quantum mechanical probability cloud. The solid, weighty, substantial feeling world you inhabit is, at its physical foundation, almost entirely empty space, and quantum fields. The substance is an illusion produced by quantum mechanical forces. The weight is an illusion produced by binding energy masquerading as mass. The solidity is an illusion produced by the Pauli exclusion principle preventing electron clouds from interpenetrating. This is the atom. This is what it is actually made of. Let me now walk you through the history of how we discovered this, because the story is one of the great intellectual journeys in human history. A journey that went from a purely philosophical idea, atoms as indivisible building blocks, through a century of experimental physics, to the extraordinarily precise and extraordinarily strange quantum mechanical picture we have today. Rutherford's discovery of the nucleus in 1909 was the first great shock. The atom was not a solid sphere. It was mostly empty, with a tiny dense core. Then came Bohr's model in 1913, with its mysterious fixed orbits. Then de Broglie's wave hypothesis in 1924. Then quantum mechanics in 1926, which replaced orbits with probability clouds and replaced certainty with inherent quantum indeterminacy. Each step was more radical than the last. Each new picture of the atom was stranger and less intuitive than the previous one, and each new picture was forced on physicists not by their preferences, but by the experimental evidence. The experiments demanded the strange conclusions. The physicists, many of them deeply uncomfortable with what the evidence was saying, had to follow it anyway. When Heisenberg developed his matrix mechanics, the first formulation of quantum mechanics, he made a deliberate choice. He would only include in his equations quantities that were, in principle, observable. Position was not observable for an electron in an atom. Only the wavelengths of light emitted and absorbed were observable. So, he built his theory from those observables and derived the electron positions as secondary derived quantities. This is why the uncertainty principle, which says you cannot simultaneously know both the position and momentum of a particle with arbitrary precision, is not just a statement about measurement limitations. It is built into the foundations of the theory. Position and momentum are not simultaneously definite. They cannot be, because the mathematics that describes quantum systems does not allow both to have definite values simultaneously. Heisenberg was 24 years old when he developed matrix mechanics. Schrödinger was 39 when he developed wave mechanics a few months later. These were young minds, willing to abandon the safe ground of classical physics and follow the mathematics wherever it led, however uncomfortable the destination. The destination was a picture of the atom in which electrons are not little balls. They are quantum fields, described by wave functions, existing in superpositions of positions, with no definite location until measured. The nucleus is not a cluster of solid billiard balls. It is a quantum mechanical bound state of protons and neutrons, themselves quantum mechanical bound states of quarks, held together by the strong force mediated by gluons, with the mass of the whole system determined more by binding energy than by the mass of the constituent quarks. The word atom means indivisible. It was named by Democritus for the smallest possible piece of matter. In one sense, Democritus was right that there are smallest building blocks. In another sense, atoms turned out to be divisible, far more divisible than he imagined, into electrons and nuclei, nuclei into protons and neutrons into quarks, and electrons and quarks into whatever lies beneath them, if anything does. Are quarks and electrons truly fundamental? Are they truly the smallest building blocks? We do not know. The standard model of particle physics, the most successful physical theory ever constructed, treats quarks and electrons as fundamental point-like particles with no internal structure. All our experiments are consistent with this, but there is no reason in principle why they could not themselves be composite, made of yet smaller constituents at scales we have not yet probed. String theory proposes that quarks and electrons are not point particles but tiny vibrating strings, with the different modes of vibration corresponding to different particles. This would mean that the hierarchy of structure goes one level deeper, but string theory is not experimentally confirmed. It is a theoretical framework with enormous mathematical beauty and enormous difficulty in making testable predictions. At the level of quarks and electrons, we are at the current frontier of our experimental knowledge. We cannot say with certainty whether there is anything smaller, but what we do know is extraordinary. Starting from the ancient Greek idea of the indivisible atom, following the evidence through 2.5 millennia of observation and experiment, we have arrived at a picture of matter that is almost impossibly strange. Matter is made of atoms. Atoms are made of electrons and nuclei. Nuclei are made of protons and neutrons. Protons and neutrons are made of quarks. And the mass of almost everything comes not from the quarks, but from the binding energy of the forces between them. The solid world is empty space. The heavy world is mostly energy. The definite, tangible, graspable world of everyday experience is built from quantum fields and probability clouds and particles with no definite position. This is what physics has found, not what we hope to find, not what we would have designed if given a choice, what is actually there, and it is breathtaking. Let me close tonight by bringing this back to you, to your hand, to the table in front of you, to the air you are breathing. Your hand is made of atoms. Those atoms are made of nuclei and electrons. The nuclei are made of protons and neutrons, which are made of quarks. By volume, the atoms in your hand are 99.999999% empty space. The actual matter, the quarks, occupy a volume so small compared to the atom that no analogy does it justice. And yet, your hand is real. It is solid in the functional sense that it cannot pass through the table. It has mass in the functional sense that gravity pulls it down. It has texture and temperature and all the properties you associate with a physical object. How can something be mostly empty and yet completely solid? How can something be mostly energy and yet have definite mass? How can the fundamental particles have no definite positions and yet produce a world of definite, graspable objects? The answer is quantum mechanics. The Pauli exclusion principle creates effective rigidity out of probability clouds. The energy of quantum fields creates effective mass out of binding energy. The decoherence of quantum states, in interaction with the macroscopic environment, creates effective definiteness out of quantum superpositions. The solid, definite, graspable world is not an illusion. It is real, but it is an emergent reality. A macroscopic consequence of quantum mechanical rules operating at the microscopic level. Rules that, at the microscopic level, produce a world nothing like the world you experience. And at the macroscopic level, through the accumulated effect of trillions of quantum interactions, produce the familiar, solid, definite world of hands and tables and cups of coffee. You are made of atoms. Atoms are made of almost nothing. And from almost nothing, the universe has constructed everything. That is the atom. That is what it is actually made of. But before you sleep, I want to go deeper into several things we move through quickly. Because the atom rewards patience. The more time you spend with it, the stranger and more beautiful it becomes. Let us go deeper into the electron. We said that the electron does not have a definite position. It exists as a probability cloud, a wave function spread through space, with no location until measured. But what does this actually mean? How can a particle have no location? Is this not just a statement about the limits of our measurement technology? No. This is the central claim of quantum mechanics, and it is not about measurement limitations. The electron genuinely does not have a position until it is measured. This is not a hidden variable waiting to be discovered. It is the actual state of the world. Here is the clearest demonstration of this. You know the double slit experiment. A single electron fired at a barrier with two slits passes through both slits simultaneously and interferes with itself. If the electron had a definite position, a definite trajectory, it would have to go through one slit or the other. It could not interfere with itself. The interference pattern is direct experimental evidence that the electron was, in the fullest sense, in two places at once. And when you set up a detector to find out which slit it went through, the interference pattern disappears. The electron, forced to have a definite position at the slit, becomes a particle and goes through one slit or the other. The act of finding out which slit it used destroys the quantum superposition that produced the interference. This means that the indefiniteness of the electron's position is not a matter of our ignorance. It is a matter of the electron's actual physical state. The electron in an atom does not have a location. It has a probability distribution. And that probability distribution is as real, as physically significant, as the electron itself. The shape of the probability distribution, the orbital, depends on the energy level the electron is in. In the lowest energy state of hydrogen, the orbital is a sphere. The electron is equally likely to be found in any direction from the nucleus, at a distance that follows a specific probability distribution peaked at a certain radius. In higher energy states, the orbitals take on the strange, elaborate shapes that you sometimes see in chemistry textbooks. Dumbbell shapes, cloverleaf shapes, toroidal shapes. These shapes are not arbitrary. They are the solutions to the Schrödinger equation for an electron in the electrical field of the nucleus. They are the quantum mechanical wave functions, the standing wave patterns of the electron wave in the potential well created by the nucleus, and they determine all the chemical properties of the atom. The way atoms bond to each other to form molecules is determined entirely by the shapes of their electron orbitals. Covalent bonds, the kind that hold hydrogen molecules and carbon atoms in organic chemistry together, form when electron orbitals from two different atoms overlap in space, creating a shared probability distribution that is lower in energy than the separate distributions. The atoms bind because sharing their electron probability clouds lowers the total energy of the system. All of chemistry, every reaction that has ever occurred, every molecule that has ever been assembled, every drug that has ever been synthesized, every protein that has ever folded, every strand of DNA that has ever been replicated, all of it follows from the quantum mechanical wave functions of electrons in atoms. The diversity of chemistry is a consequence of the diversity of orbital shapes and the rules that govern how they interact. This is one of the most beautiful things in science. The quantum mechanical description of the atom, arrived at in the 1920s, immediately explained not just atomic spectroscopy, but the entire foundation of chemistry. Why elements have the properties they do, why the periodic table has the structure it does, why some atoms bond readily and others do not, why some materials conduct electricity and others do not. Before quantum mechanics, chemistry was a collection of empirical rules and regularities that no one could explain from first principles. After quantum mechanics, it was a branch of physics. Every chemical property followed, in principle, from the Schrödinger equation. Now, let us go deeper into the nucleus. The nucleus is not just a static collection of protons and neutrons. It is a quantum mechanical bound state, governed by the same principles of wave functions and probability distributions that govern electrons. Protons and neutrons inside a nucleus also have orbital-like quantum states. They also have probability distributions rather than definite positions. They also obey the Pauli exclusion principle. The Pauli exclusion principle applies to protons among protons and to neutrons among neutrons. Each proton must be in a different quantum state from every other proton. Each neutron must be in a different quantum state from every other neutron. This creates a shell structure in the nucleus, analogous to the shell structure of electrons in atoms. Nuclei with certain numbers of protons or neutrons fill their quantum shells completely and are particularly stable. These are called magic numbers. Nuclei with magic numbers of protons or neutrons, or especially both, are among the most stable in nature. The most doubly magic nucleus is lead 208, with 82 protons and 126 neutrons, both magic numbers, making it one of the most stable heavy nuclei known. The shell structure of nuclei explains patterns in nuclear stability that otherwise would seem arbitrary, why some nuclei are stable and others decay, why certain isotopes last for billions of years and others for fractions of a second. All of it follows from the same quantum mechanical principles that explain the electron shells in atoms. Nuclear decay, when it occurs, is also a quantum mechanical phenomenon. Alpha decay, in which a nucleus emits a package of 2 protons and 2 neutrons, is a quantum tunneling process. The alpha particle exists in some sense inside the nucleus, but the nuclear potential is like a wall surrounding it. Classically, the alpha particle does not have enough energy to escape over the wall, but quantum mechanically, there is a finite probability that it will tunnel through the wall. This probability is extremely small for stable nuclei, but finite. And over long enough time, the tunneling occurs and the nucleus decays. Quantum tunneling is one of the strangest phenomena in quantum mechanics. It allows particles to pass through barriers that they classically could not surmount, and it has consequences far beyond nuclear physics. The transistors in every computer you have ever used work by quantum tunneling. The nuclear fusion in the core of the sun occurs at temperatures far lower than the classical calculation would require, because protons tunnel through the electromagnetic barrier between them. Without quantum tunneling, the sun would not shine. Without quantum tunneling, there would be no electronics. Without quantum tunneling, there would be no US. The atom is the foundation of all of this. Not the classical atom of Dalton or the semi-classical atom of Bohr. The full quantum mechanical atom with its probability clouds and its tunneling and its Pauli exclusion and its shell structures. The atom that emerged from the physics of the 1920s and has been refined and extended ever since. Let me now tell you about something that sits at the very frontier of our understanding of atoms and the particles inside them. The question of what gives particles their mass. We know that quarks have mass, electrons have mass, protons have mass, mostly from the binding energy of the quarks inside them. But where does the mass of the quarks and electrons come from? Why do they have the masses they have, rather than different masses, or no mass at all? The answer, according to the standard model of particle physics, involves a field that permeates all of space, the Higgs field. The Higgs field interacts with quarks and electrons, giving them their mass. A particle that interacts strongly with the Higgs field acquires a large mass. A particle that does not interact with the Higgs field at all, like the photon, has no mass. The Higgs field was proposed by Peter Higgs and others in 1964 as part of the mechanism for giving mass to the W and Z bosons, the carriers of the weak nuclear force. Without mass, those bosons would travel at the speed of light, and the weak force would behave like electromagnetism. With mass, the weak force has a short range, consistent with what is observed. The Higgs field also gives mass to quarks and electrons through a process called Yukawa coupling. The strength of the coupling determines the mass. Different quarks have different coupling strengths, and hence different masses. The top quark, the heaviest of the 6 quarks, has a mass about 173 times the proton mass, because it couples to the Higgs field much more strongly than any other quark. The Higgs boson, the particle associated with the Higgs field, was discovered at CERN in 2012 after a search that lasted decades and required the construction of the largest and most complex scientific instrument in human history, the Large Hadron Collider. The discovery was one of the great triumphs of experimental physics. It confirmed the existence of the Higgs field and validated the core of the standard model, but it also raised new questions. Why do different particles couple to the Higgs field with different strengths? Why do the quarks and leptons have the masses they have, rather than different masses? Why does the Higgs field have the strength it has? These questions are not answered by the standard model. They are some of the most pressing open questions in particle physics. The atom, which seemed to the ancient Greeks to be the simplest, most fundamental thing in nature, has turned out to be a gateway to an extraordinary depth of structure and mystery. Every time physicists have looked more closely, they have found more. The atom has electrons and a nucleus. The nucleus has protons and neutrons. The protons and neutrons have quarks and gluons. The quarks have mass from the Higgs field, and beneath that, we do not know what lies. This progression, from atom to nucleus to quarks to Higgs field, is one of the most remarkable journeys in the history of science. It has taken us from the kitchen table chemistry of the 19th century to the Large Hadron Collider of the 21st. From Dalton weighing gases to thousands of physicists from dozens of countries collaborating to build the most complex machine ever constructed. And at every step, what we found was stranger than what we expected, stranger than what we would have imagined, stranger than what common sense prepared us for, but always consistent, always following the mathematical rules, always producing predictions that match the experiments with extraordinary precision. The standard model of particle physics is the most precisely tested theory in the history of science. Its predictions have been confirmed to more decimal places than any other physical theory. The magnetic moment of the electron, the most precisely measured quantity in physics, agrees with the standard model's prediction to 11 decimal places. 11. That is like measuring the distance from New York to Los Angeles to within a fraction of the width of a human hair. This is what the atom has led us to. From Democritus's philosophical speculation to the most precise quantitative theory ever created. 2,500 years of asking what matter is made of, arriving at an answer that Democritus could not have imagined, and that we ourselves still do not fully understand. Because the standard model, precise as it is not complete. It does not include gravity. It does not explain why there is more matter than antimatter in the universe. It does not explain what dark matter is. It does not explain the values of its own parameters, the masses of the quarks, the strengths of the forces, the properties of the Higgs field. Physics knows it is not done. The atom has given us enormous insight, but the atom is still, at its deepest level, not fully understood. And that is not a failure, that is an invitation. Let me close with one final thought about what all of this means for the experience of being here, of being a physical object in a physical world. You are made of atoms, about 7 billion of them, mostly hydrogen, oxygen, carbon, nitrogen, with smaller amounts of other elements. Each of those atoms is mostly empty space. Each of those atoms contains a nucleus, whose mass comes mostly from binding energy, rather than from the mass of its quarks. Each of those atoms has electrons that exist as probability clouds rather than as classical particles. You are mostly empty space. You are mostly energy. You are mostly quantum probability. And yet, you are entirely, completely, unmistakably real. The solidity you feel is real. The weight you carry is real. The warmth of your body is real. All of it emerges from the quantum mechanical interactions of particles that have no classical description. All of it is produced by forces that operate at scales 1 billion times smaller than anything you can see. All of it is a macroscopic consequence of quantum mechanics operating at the microscopic level, producing, through the combined effect of an astronomical number of interactions, the ordinary, familiar, solid world you inhabit. This is what physics has found. Not what we expected, not what we would have designed, what is actually there. And it is, in every way that matters, more extraordinary than the simple picture that was stuck in your head since childhood. The atom is not a solar system in miniature. It is something far stranger, far richer, far more complex and beautiful and counterintuitive than that. And now you know what it actually is. But I want to go further. Because there are things about the atom that we have not yet touched, things that connect it to your everyday experience in ways that most people never realize, and things that sit at the frontier of current research in ways that will shape the future. Let me take you through the periodic table, because the periodic table is not just a chart on a chemistry classroom wall. It is the direct consequence of quantum mechanics applied to atoms. Every pattern in the periodic table, every group of elements that behave similarly, every trend in atomic size or ionization, energy or chemical reactivity, follows from the quantum mechanical structure of electron orbitals. The periodic table is quantum mechanics made visible. Here is how it works. Electrons in an atom occupy orbitals of increasing energy. The lowest energy orbitals are filled first. Each orbital can hold a maximum of 2 electrons, with opposite spins. Because of the Pauli exclusion principle, the number and arrangement of electrons in the outermost occupied orbitals, the valence electrons, determines the chemical behavior of the element. Hydrogen has 1 electron in its lowest orbital. It can either give that electron away, becoming a positive ion, or share it with another atom, forming a covalent bond. This is why hydrogen is so reactive, why it burns in air, why it combines readily with oxygen to form water. Helium has 2 electrons, filling the lowest orbital completely. It has no desire to gain or lose electrons. It is chemically inert, noble, unreactive. This is why helium does not combine with anything under ordinary conditions. Its electron configuration is complete and perfectly stable. Lithium has 3 electrons. 2 fill the lowest orbital. The third is alone in the next orbital, easily given away. So lithium is highly reactive, easily losing its outermost electron to form a positive ion. It is a metal with strong chemical reactivity. This pattern continues through the entire periodic table. The arrangement of electrons in orbitals, following quantum mechanical rules, produces the chemical personalities of every element. The noble gases, helium, neon, argon, krypton, xenon, radon, all have completely filled outer shells and are chemically inert. The alkali metals, lithium, sodium, potassium, rubidium, cesium, all have 1 electron in their outer shell and are extremely reactive. The halogens, fluorine, chlorine, bromine, iodine, all have 7 electrons in their outer shell, 1 short of a complete shell, and are highly reactive in the opposite direction, eager to gain an electron. All of this regularity, all of this pattern, all of this beautiful organization follows from the quantum mechanical rules governing the electron orbitals of atoms. The periodic table is a map of quantum mechanics. Every box in it represents an element whose chemical behavior is determined by the shape and occupancy of its electron orbitals. The fact that quantum mechanics, developed in the 1920s to explain spectroscopic data and the behavior of single electrons, immediately explained the entire organization of the periodic table, was one of the most stunning confirmations of the theory. Chemistry, which had seemed to be a completely separate discipline from physics, was revealed to be a branch of quantum mechanics. The boundary between the two disciplines was dissolved. Now, let me take you into territory that is rarely discussed in popular accounts of the atom, the question of what atoms are doing most of the time. Not in special experimental conditions, but in ordinary matter, at room temperature, in the world you actually inhabit. Atoms in a solid are not sitting still. They are vibrating. The bonds between atoms in a solid are not rigid connections. They are more like springs, elastic connections that allow the atoms to oscillate around their equilibrium positions. At any temperature above absolute zero, these oscillations are present. At room temperature, atoms in a solid are vibrating at roughly 10 trillion times per second. They do not move very far, only a tiny fraction of the atomic spacing, but they are constantly in motion. These vibrations carry energy. The energy of atomic vibrations is what we call heat. Temperature is a measure of the average kinetic energy of the atoms in a material. When you heat something up, you are making its atoms vibrate faster and with larger amplitude. When it cools down, the vibrations slow. At absolute zero, the vibrations reach their minimum, but they never stop completely. Even at absolute zero, quantum mechanics requires a minimum residual vibration called the zero-point energy. Atoms cannot be perfectly still. The zero-point energy is another consequence of the uncertainty principle. If an atom were perfectly still, its position would be fixed, and its momentum would be exactly zero. But you cannot know both position and momentum precisely. A perfectly still atom would have perfectly known momentum and perfectly known position, violating the uncertainty principle. So, atoms must always be slightly uncertain in their position, which means they must always be vibrating slightly, even at absolute zero. This zero-point motion has real physical consequences. It is why helium, under ordinary pressure, does not solidify even at absolute zero. The zero-point vibrations of helium atoms are large enough to prevent them from locking into a crystal lattice. Helium remains liquid at absolute zero, at atmospheric pressure. Only under pressure does it solidify. It is the only element that exhibits this behavior. In liquids, the atoms are also moving, but not around fixed positions. They slide past each other, maintaining short-range order, but no long-range crystalline structure. The motion is more complex, with atoms constantly rearranging, forming and breaking bonds, diffusing through the liquid. At the molecular level, a glass of water is a constant dynamic rearrangement of hydrogen and oxygen atoms. Hydrogen bonds forming and breaking at a rate of trillions of times per second. In a gas, the atoms or molecules are far apart, moving rapidly in all directions, colliding with each other and with the walls of any container. The pressure that a gas exerts on its container is the cumulative effect of the forces of all those collisions, each individual atom bouncing off the wall and transferring a tiny impulse. All of this motion, this constant vibrating, sliding, bouncing dynamic activity, is the atomic reality underlying the apparently static world you see. The chair looks still. Its atoms are vibrating at 10 trillion times per second. The water looks calm. Its molecules are rearranging at rates that dwarf human comprehension. The air looks empty. It contains about 25 million atoms in every cubic centimeter, each moving at an average speed of several hundred meters per second, each colliding with other atoms billions of times per second. The apparent stillness and solidity of the macroscopic world is a statistical average over this extraordinary microscopic activity. The solid that does not visibly vibrate is made of atoms vibrating at rates beyond any human perception. The liquid that flows smoothly is made of atoms in constant rapid rearrangement. The gas that fills a room evenly is made of atoms in constant rapid random motion. You are made of atoms in constant rapid random motion. Your body is not a static structure. It is a dynamic, constantly rearranging assembly of molecules, each made of atoms, each atom with its vibrating nucleus and its surrounding probability cloud of electrons. Every moment, atoms in your body are moving, reacting, binding, releasing. Proteins are folding and unfolding. DNA is being read and replicated. Ions are flowing through channels in cell membranes. Neurotransmitters are diffusing across synaptic gaps. All of it, at the atomic level, is quantum mechanics playing out in real time in the cells and tissues and fluids of your body. You are not a thing, you are a process. A quantum mechanical process maintained far from thermodynamic equilibrium by the constant input of chemical energy from food and oxygen, producing the extraordinary organized complexity of a living body out of the ordinary laws of quantum mechanics applied to atoms. Let me also take you into one of the most important applications of atomic physics, something that has saved more human lives than any other technology in the last century: medical imaging. X-rays, discovered by Wilhelm Röntgen in 1895, work by passing high-energy photons through the body and detecting how they are absorbed differently by different tissues. Bone, which is dense with calcium atoms, absorbs X-rays strongly. Soft tissue, which is mostly water and carbon-based molecules, absorbs them less strongly. The difference produces a shadow image of the internal structure of the body, but X-rays only show shadows. They show density differences, not detailed structure. For detailed imaging of soft tissue, medicine needed a different approach. Magnetic resonance imaging, MRI, works directly with atomic nuclei, specifically with the nuclei of hydrogen atoms, which are single protons. Every water molecule contains 2 hydrogen atoms. Every fat molecule contains many hydrogen atoms. Your body is largely composed of water and fat. It contains an enormous number of hydrogen nuclei. Protons have a quantum mechanical property called spin, which is a form of intrinsic angular momentum with no classical analog. Spin is quantized. It can be either up or down relative to any chosen direction. In the presence of a strong magnetic field, protons with spin up have a slightly different energy than protons with spin down. By applying radio frequency electromagnetic pulses, you can flip the spins of protons from one orientation to the other. When the protons flip back, they emit radio waves at a specific frequency. By carefully analyzing the pattern of emitted radio waves, you can construct a detailed 3-dimensional image of the distribution of hydrogen nuclei in the body. Since hydrogen is concentrated in water and fat, and different tissues contain different amounts of water and fat, the MRI image reveals the internal soft tissue structure of the body with extraordinary detail. Brain structure, muscle, tumors, inflammation, blood flow, all of it visible in MRI, all of it based on the quantum mechanical properties of atomic nuclei. MRI is a direct application of quantum mechanics to atomic nuclei, producing a medical technology that has transformed diagnosis and saved millions of lives. Every MRI machine is, at its core, a device that exploits the quantum spin of protons in hydrogen nuclei. PET scanning, positron emission tomography, works with the quantum mechanical process of radioactive decay. A patient is injected with a substance that is chemically identical to glucose, but contains a radioactive isotope that emits positrons, the antimatter counterpart of electrons. As the substance concentrates in metabolically active tissue, the positrons emitted by the radioactive isotope annihilate with electrons in the surrounding tissue, producing gamma rays that are detected by the scanner. The pattern of gamma rays reveals where metabolic activity is highest. Brain activity, cancer metabolism, heart function can all be imaged in this way. Both MRI and PET scanning are entirely dependent on atomic physics, on the quantum mechanical properties of atomic nuclei and particles, on the radioactive decay processes that are governed by the same quantum mechanical tunneling we discussed in the context of alpha decay. The atom, which seemed like the ultimate frontier of the unimaginably small, is now routinely exploited by medicine to see inside the human body in extraordinary detail. Now, let me close with something that brings all of this together and puts it in the largest possible context. Everything you see in the night sky, every star, every galaxy, every nebula, every cluster of matter in the observable universe is made of atoms, the same quantum mechanical structures, the same electrons in the same orbital configurations. the same protons and neutrons made of the same quarks held by the same gluons, the same physics. The hydrogen atoms in the most distant galaxy are identical to the hydrogen atoms in your body. They have the same electron orbital, the same proton mass, the same quantum mechanical wave function. The same Schrödinger equation with the same constants describes them both. The universe is made of the same stuff everywhere. This universality of atoms is one of the most remarkable facts in science. There is no place in the observable universe where physics works differently. No place where atoms have a different structure. No place where the quantum mechanical rules are different. The same physics that describes the atom in your hand describes the atoms in the most distant quasar, 13 billion light years away. The elements in your body were not always in your body. Before they were part of you, they were part of other organisms, other environments, other geological formations. Before that, they were forged in the cores of stars. The carbon in your cells, the oxygen you breathe, the calcium in your bones, the iron in your blood, all of it was synthesized in stellar interiors through nuclear fusion reactions driven by the strong force and the gravity of massive stars. When those stars died, often in spectacular supernova explosions, they scattered their contents into space. Those contents, drifting through the galaxy for millions of years, eventually condensed into new stars and planets. One of those planets was Earth. And on Earth, over billions of years, chemistry built biology, and biology built you. You are made of atoms that were forged in stars. The iron in your blood was forged in the core of a massive star that died before the sun was born. The carbon in your DNA was assembled from the ashes of multiple stellar generations. You are, in the most literal physical sense, made of stardust. And those atoms, which traveled for billions of years across interstellar space, which were part of countless other structures before they were part of you, carry within them the quantum mechanical structure that makes them what they are. The electron orbitals that make carbon bond to 4 other atoms. The nuclear structure that makes iron magnetic. The proton configuration that makes hydrogen so reactive with oxygen. All of this quantum mechanical structure, forged in the Big Bang and in stellar interiors, has been carried across billions of years and billions of light years to be here, now, in you. You are not separate from the universe. You are made of the universe, assembled from its atoms, governed by its physics, participating in its ongoing evolution. The atom is the bridge between the subatomic world of quarks and the cosmic world of galaxies. And you are made of atoms, which makes you a physical embodiment of that bridge. That is the atom. That is what it is made of. That is what you are made of. Before we close, there are a few more layers of the atom's story that deserve your attention. Things that connect atomic physics to the largest questions in modern science and to the most immediate questions about the world you live in. Let us talk about antimatter. Every particle in the atom has an antiparticle. The electron has the positron, identical in mass but opposite in charge. The proton has the antiproton. The neutron has the antineutron. Quarks have antiquarks. When a particle meets its antiparticle, they annihilate, converting all their mass into energy in the form of photons or other particles. In the first moments after the Big Bang, matter and antimatter were created in equal amounts from the pure energy of the early universe. If the universe had remained perfectly symmetric, every particle would eventually have met its antiparticle and annihilated, leaving a universe of pure radiation and nothing else. No atoms, no stars, no galaxies, no us. But we exist, which means that, somehow, a tiny excess of matter over antimatter survived the annihilation. For every billion pairs of particles and antiparticles that annihilated in the early universe, there was one extra particle of matter. That tiny excess, 1 part in a billion, is everything we see today. Every atom in your body, every star in every galaxy, every planet and moon and asteroid and nebula in the observable universe. All of it is the 1 in a billion survivor of the great matter-antimatter annihilation of the early universe. Why was there that tiny excess? Why was the universe not perfectly symmetric? This is one of the most important unsolved problems in physics. The Standard Model does contain CP violation, the subtle asymmetry between matter and antimatter that we discussed in the context of the arrow of time. But the amount of CP violation in the Standard Model is not enough, by many orders of magnitude, to explain the observed matter-antimatter asymmetry in the universe. Something beyond the Standard Model must be responsible. What the something is, we do not yet know. The search for the source of the matter-antimatter asymmetry is one of the driving motivations for experiments at the Large Hadron Collider and at dedicated facilities like the Belle 2 experiment in Japan, which studies the properties of particles called B mesons, which contain bottom quarks, in search of new sources of CP violation. Every atom in your body exists because of this mystery. You are the product of the matter-antimatter asymmetry of the early universe. And that asymmetry is not yet explained. Let me also take you into the quantum field theory perspective on atoms, because it gives a picture of what atoms really are that goes beyond even what we have discussed so far. In quantum field theory, the most fundamental description of nature that we have, particles are not the fundamental objects. Fields are. Space is permeated by quantum fields, one for each type of particle. There is an electron field, a quark field, a photon field, a gluon field, a Higgs field. These fields fill all of space. They exist everywhere, even in regions we think of as empty. Particles, in quantum field theory, are excitations of these fields. An electron is not a tiny ball. An electron is a localized excitation of the electron field, a small disturbance in the field that propagates through space according to quantum mechanical rules. A photon is an excitation of the photon field. A quark is an excitation of the quark field. The atom, in this picture, is not a collection of particles. It is a complex bound excitation of multiple fields. The electrons are excitations of the electron field, bound to the nucleus by the electromagnetic interaction, which is mediated by the photon field. The quarks in the nucleus are excitations of the quark fields, bound by the strong interaction, which is mediated by the gluon field. And the mass of the quarks comes from their interaction with the Higgs field, which is itself a field permeating all of space. This field-theoretic picture reveals something profound about what matter is. Matter is not made of things. It is made of fields. The excitations of those fields produce what we call particles. The interactions between those fields produce what we call forces, and the bound states of those excitations produce what we call atoms. Empty space in quantum field theory is not empty. It is filled with quantum fields in their ground states, the lowest energy configuration. These ground states are not perfectly still. Quantum uncertainty means they fluctuate, constantly, creating and destroying virtual particles in a constant, invisible quantum jitter. This jitter is called the quantum vacuum, and it has real physical effects. The Casimir effect, the tiny attractive force between two neutral metal plates placed very close together in a vacuum, is a direct consequence of the quantum vacuum. The presence of the plates restricts the vacuum fluctuations between them, creating a slight pressure difference that pushes the plates together. This effect has been measured and agrees with quantum field theory predictions. Empty space is not empty. It is a dynamic, fluctuating quantum medium. The quantum vacuum also contributes to the masses of particles. Particles interacting with the vacuum fluctuations acquire corrections to their masses, called self-energy corrections. The precise masses of quarks and electrons in the Standard Model include these quantum vacuum contributions. Calculating them requires the technique of renormalization, developed in the late 1940s by Richard Feynman, Julian Schwinger, and Shinichiro Tominaga, who shared the Nobel Prize in Physics in 1965 for this work. All of this, the field-theoretic picture, the quantum vacuum, the self-energy corrections, lies beneath the atom. It is the quantum field theory substrate on which atomic physics rests, and it reveals that the atom, seemingly the simplest unit of matter, is connected to the deepest structures of the physical world. Let me also tell you about something that connects atomic physics directly to the future of technology: quantum computing. The electron in an atom can be in different quantum states. The spin of an electron can be up or down. The orbital of an electron can be in the ground state or an excited state. These quantum states can be used to store information. A quantum bit, or qubit, is a quantum system that can be in a superposition of two states, 0 and 1, just as a classical bit can be 0 or 1, but with the crucial difference that a qubit can be in both 0 and 1 simultaneously. in a quantum superposition. This superposition allows quantum computers to process information in ways that classical computers cannot. A quantum computer with 100 qubits can represent 2 to the power of 100 states simultaneously. Operations performed on this quantum state can, in principle, explore an exponentially large space of possibilities in parallel. The atoms and their quantum states are the building blocks of quantum computing. Several types of quantum computers use atoms directly. Trapped ion quantum computers use individual atoms, ions, confined in electromagnetic traps as their qubits. The quantum states of the ions, their internal energy levels, or their spin states, encode the quantum information. Operations are performed by shining laser light on the ions, inducing quantum transitions between states. Neutral atom quantum computers use arrays of individual neutral atoms, trapped in arrays of focused laser beams called optical tweezers, as their qubits. The precise control over individual atoms that modern atomic physics allows makes it possible to build highly controlled quantum systems with dozens or hundreds of qubits. The atom, which was discovered to be divisible into electrons and nuclei, which turned out to contain quarks and gluons, which turned out to be excitations of quantum fields, is now being used as a fundamental unit of quantum information processing. The quantum mechanical strangeness of the atom, its superpositions, its entanglement, its tunneling, which once seemed like mere curiosities of the subatomic world, are now the active ingredients of the most powerful computing technology ever conceived. The atom has given us an extraordinary journey. From the ancient Greek idea of the indivisible, through the discovery of electrons and nuclei, through quantum mechanics and quarks and the Standard Model and quantum field theory, to quantum computers and MRI scanners and nuclear medicine and the explanation of the entire periodic table. And through all of it, the atom has kept showing us that nature is stranger and richer and more surprising than we expected. Every time we thought we understood it, it opened a new layer. Every time we thought we had found the bottom, there was more below. This is what the atom is, not just a building block of matter, a gateway to the deepest questions in physics, a window into the quantum world, a bridge between the human scale and the cosmic scale, and a reminder that the solid, ordinary, familiar world you inhabit is built from something extraordinary. You are made of atoms. Atoms are made of almost nothing. And from almost nothing, held together by quantum fields and forces so strange that even the physicists who work with them daily still find them astonishing, the universe has built everything. Let me now walk you through the human stories behind atomic physics. Because these discoveries did not emerge from equations alone. They emerged from specific people, wrestling with specific experiments, often facing enormous skepticism. Ernest Rutherford was born in New Zealand in 1871, one of 12 children of a farmer. He won a scholarship to Cambridge, worked under J. Thomson, the discoverer of the electron, and went on to do his greatest work at Manchester. When his gold foil experiment showed that the atom had a tiny, dense nucleus, it completely overthrew his mentor, Thomson's plum pudding model. Rutherford did not hesitate. The data was clear. He published his nuclear model in 1911. Rutherford had an extraordinary ability to attract brilliant students. Niels Bohr worked with him at Manchester. James Chadwick, who discovered the neutron, was his student. Hans Geiger, who co-invented the Geiger counter, was his student. Rutherford's laboratory was one of the most productive research environments in the history of physics. Niels Bohr, who developed the first quantum model of the atom, had no theoretical justification for his rule that electrons could only occupy certain orbits. He imposed it because it worked. His willingness to adopt an empirical rule without a theoretical basis, to put experimental facts ahead of theoretical purity, was characteristic of his genius. When Germany occupied Denmark in 1940, Bohr's position became dangerous. In 1943, warned he was about to be arrested, he escaped by boat to Sweden and then by aircraft to Britain. He spent the last years of his life advocating for international control of nuclear technology. Werner Heisenberg was 23 years old when he developed matrix mechanics on the island of Helgoland, where he had retreated to recover from hay fever. He later recalled that when he saw the mathematical implications of what he had done, he felt a deep unease. The mathematics was working too well. He was looking into a landscape he barely understood. Erwin Schrödinger was 39 when he developed wave mechanics during a Christmas vacation in the Swiss Alps. He was so disturbed by the probabilistic interpretation that others gave his equation that he later said, if he had known where it would lead, he might never have published it. These brilliant, complicated human beings, living through the most turbulent period in human history, produced one of the most profound intellectual revolutions in the history of science. The atom they revealed is not what anyone expected. It is stranger and richer and more beautiful than the simple building block that Democritus imagined 2,500 years ago, and it is still, at its deepest levels, not fully understood. There are genuine open questions. Why do quarks have the masses they have? Is the proton truly stable, or does it decay over timescales far longer than the age of the universe? What lies beneath quarks and electrons, if anything? These questions are being actively investigated. The atom is not a solved problem. It is a frontier. And from this extraordinary, counterintuitive, deeply strange quantum mechanical structure, the universe has built everything you have ever touched, seen, tasted, and loved. Every star, every planet, every molecule of air in your lungs, every neuron firing in your brain right now, from almost nothing. Held together by quantum fields and forces so strange they still astonish the people who work with them every day. I want to give you one more layer before tonight truly ends, because we have covered the structure of the atom and the history of its discovery and the human stories behind it. But we have not yet talked about what happens when atoms interact with light. And that story is one of the most beautiful in all of physics. When light strikes an atom, one of several things can happen depending on the energy of the photon. If the photon has exactly the right energy, an electron can absorb it and jump from a lower energy orbital to a higher one. The electron is now in an excited state. It does not stay there long. After a tiny fraction of a second, typically around 1 nanosecond, it falls back down to the lower energy state and emits a new photon with exactly the same energy as the one it absorbed. This process, called fluorescence or spontaneous emission, is responsible for an enormous range of phenomena. The colors of neon signs come from electrons in neon atoms being excited by electrical discharge and then falling back to lower states, emitting photons of specific wavelengths corresponding to the specific energy differences between the orbitals of neon. The wavelengths of these photons, and hence the colors produced, are uniquely characteristic of each element. Neon glows red-orange, mercury glows blue-white, sodium glows yellow. This characteristic color emission is the atomic fingerprint. Every element emits light at a unique set of wavelengths when its electrons are excited. These wavelengths form a spectrum that is as unique to each element as a fingerprint is to a person. By analyzing the light emitted by a distant star, astronomers can determine the chemical composition of that star. The dark lines in the solar spectrum, called Fraunhofer lines, are absorption lines produced by atoms in the cooler outer layers of the sun, absorbing specific wavelengths of the light produced in the hotter interior. Each dark line corresponds to a specific atomic transition in a specific element. From these lines, astronomers can determine that the sun contains hydrogen, helium, carbon, nitrogen, oxygen, iron, and dozens of other elements, all without ever visiting it. The discovery that each element has a unique spectral fingerprint was one of the great achievements of 19th century science, and the explanation of why each element has its unique spectrum, in terms of the allowed quantum energy levels of its electrons, was one of the first triumphs of quantum mechanics. When Bohr calculated the spectral lines of hydrogen from his model of quantized orbits in 1913, the agreement with observation was exact. Every line in the hydrogen spectrum, every wavelength at which hydrogen absorbed or emitted light, matched a transition between specific allowed energy levels in Bohr's model. This was the moment when quantum mechanics, still in its infancy, proved that it was describing something real. The energy levels were real, the transitions were real, the photons were real, and the atom had the structure that quantum mechanics said it had. There is also a process called stimulated emission, in which a photon of exactly the right energy can cause an excited atom to emit a second photon, rather than waiting for spontaneous emission. The second photon is identical to the first, with exactly the same wavelength, direction, and phase. Einstein predicted this process in 1917. Stimulated emission is the basis of the laser. In a laser, a large number of atoms are excited to a higher energy state by some external energy source. Then, a photon of exactly the right energy is introduced. It stimulates the emission of a second photon. Both photons then stimulate the emission of more photons. A cascade of identical photons builds up, all with the same wavelength, direction, and phase, forming an intense, coherent, highly directed beam of light. The laser is perhaps the most direct practical application of atomic quantum mechanics. It works by exploiting the precise, discrete energy levels of atoms and the quantum mechanical process of stimulated emission. Lasers are used in medicine, manufacturing, communication, data storage, scientific research, and 100 other applications. Every time a laser scans the barcode on something you buy, every time a laser pointer draws a red dot on a screen, every time a fiber optic communication system transmits data, atomic quantum mechanics is at work. There is also the phenomenon of atomic clocks, which exploit the precision of atomic transitions in a different way. The cesium atom has a specific transition between two very closely spaced energy levels in its ground state, with a frequency of exactly 9,192,631,770 oscillations per second. This transition frequency is extraordinarily stable and can be measured with extraordinary precision. The international standard for the second is defined as exactly 9,192,631,770 periods of the radiation, corresponding to this transition in cesium, 133. An atomic clock counts these oscillations and uses them to define time. The best atomic clocks are accurate to about 1 second in 300 million years. They are the most precise measuring instruments ever built. Atomic clocks are used in GPS navigation, in the synchronization of communications networks, in the definition of the International Time Standard, and in fundamental physics research. Every time you look at the time on your phone, the time has ultimately been measured by atomic transitions in cesium atoms. The atom has given us the laser and the atomic clock and the MRI scanner and quantum computers and the explanation of the periodic table and the nuclear power that generates a significant fraction of the world's electricity. All of this from understanding what atoms are made of and how they work, and all of it rests on the quantum mechanical picture that replaced the solar system model that was stuck in your head since childhood. Let me close with something about scale, because one of the things that makes the atom so hard to truly feel is that the scales involved are so far beyond ordinary human experience that analogies can barely capture them. The hydrogen atom is about 1 angstrom across, 1 angstrom, 10 to the minus 10 meters. A human hair is about 1,000,000 angstroms wide. If you could stack hydrogen atoms end to end, it would take about 1,000,000 of them to span the width of a human hair. That already feels impossibly small. But the nucleus of the hydrogen atom, the single proton at its center, is about 1 femtometer across. 1 femtometer is 10 to the minus 15 meters. The proton is 100,000 times smaller than the atom. If the atom were the size of a football stadium, the proton would be a pea at the center of the field. The quarks inside the proton are smaller still, smaller than the current limits of our experimental resolution, smaller than 10 to the minus 19 meters. At least 10,000 times smaller than the proton itself. If the proton were the size of a football stadium, the quarks would be smaller than a grain of sand. And the electron, despite having a mass, appears to be a true point particle with no measurable size at all. Experiments have probed the electron down to scales of 10 to the minus 18 meters and found no evidence of internal structure. The electron, as far as we can tell, is a geometric point, a location in the electron field with no spatial extent, so the atom is a vast, mostly empty structure, spanning the incredible range from the point-like electron to the nucleus to the full extent of the electron probability cloud, all governed by quantum mechanical rules that produce the apparently solid world you experience. Your hand contains about 10 to the 27th atoms, that is 10 followed by 27 zeros, 1 billion 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 atoms in your hand, each one following quantum mechanical rules, each one mostly empty, each one contributing to the solidity and mass and chemical properties of your hand through the accumulated quantum effects of an astronomical number of interactions. This is the world. This is what it is made of. And knowing it, really knowing it, changes something in the way you experience the apparently ordinary fact of a hand, a table, a room, an atmosphere, a planet. The ordinary is not ordinary. The familiar is not familiar, not at its foundation. The world you inhabit is, at its most fundamental level, a quantum mechanical phenomenon, as strange and as beautiful as anything the universe contains. You are made of atoms. Atoms are made of almost nothing, and from almost nothing, the universe has made everything. There is one last thing I want to say, and it is the simplest thing of all. Look at your hand. The hand you are looking at is real. It is solid, warm, capable of feeling and grasping and creating. It has carried you through your life. It has touched the people you love. It is built and written and held. And it is made of atoms, about 10,000 trillion of them, each one an extraordinary quantum mechanical structure, 99.99999% empty space, held together by invisible quantum fields. Its electrons existing as probability clouds rather than definite particles. Its mass coming mostly from the binding energy of quarks rather than from matter itself. This hand that feels so solid and definite and real is, at its foundation, almost entirely nothing. Quantum fields and probability distributions and binding energy, assembled by the laws of physics into something that you experience as a hand. That is not a diminishment of your hand. It is not a reason to feel that the hand is less real or less yours. It is a reason to feel that physics is extraordinary, that the laws of nature, applied to almost nothing, produce hands and faces and thoughts and experiences and the full richness of the world. The atom did this. The quantum mechanics of the atom did this. Starting from fields and probabilities and binding energies, following rules that no one designed and that no one fully understands, the universe built everything, including you, including this moment, including the feeling of your own hand, solid and warm, resting in your lap as you fall asleep. I want to leave you with a thought about what it means to know something this deep about the world. Most of human history passed without anyone knowing what atoms were. Democritus guessed their existence. Dalton inferred their existence from chemistry. Thomson, Rutherford, Bohr, Heisenberg, Schrödinger, Pauli, Dirac, a handful of brilliant people in a single century, working with instruments and mathematics and each other, followed the evidence to a picture of reality that is both more precise and more strange than anything that came before. You are alive in the century after that revolution. You are alive at a time when the quantum mechanical picture of the atom is not just accepted, but used daily in medicine and technology and fundamental research. When atomic clocks define the international standard of time, when MRI scanners see inside the body, using the quantum properties of hydrogen nuclei, when quantum computers beginning to harness the strangeness of electron states to perform calculations beyond classical reach, you inherited this knowledge. You did not have to derive it. You did not have to fight for it against the resistance of established ideas. It is simply available to you, part of the civilization you were born into. That is an extraordinary gift. The accumulated insight of thousands of years of human inquiry handed to you by people who came before you, asking the simple question of what matter is made of and following it wherever it led. Tonight, you received a part of that gift. The atom is not a solar system. It is a quantum mechanical miracle. Almost nothing, assembled by the laws of nature, into everything. Carry that with you. Physics began with people looking at the world and asking why it was the way it was, why things fell, why fire burned, why the sky was blue. And it arrived, after thousands of years of asking, at the atom, at quantum mechanics, at the extraordinary counterintuitive, precisely confirmed picture of matter that we have explored tonight. Every generation added something. Every generation corrected something. Every generation found that the world was stranger than the previous generation had imagined, and every generation handed what they found to the next. Democritus handed us the idea of the atom. Dalton handed us the chemical evidence. Thomson handed us the electron. Rutherford handed us the nucleus. Bohr handed us the quantum energy levels. Heisenberg and Schrödinger handed us quantum mechanics. Pauli handed us the exclusion principle. Gell-Mann handed us the quarks. The builders of the Large Hadron Collider handed us the Higgs boson. Each discovery opened new questions. Each answer pointed toward new mysteries. The atom is not at the bottom. It is a level in a hierarchy that continues downward and whose bottom we have not yet found. That continuation, that endless opening of new questions, is not a failure of physics. It is what physics is. It is what science is. The permanent, generative, unstoppable practice of asking what is really there. Tonight, you asked. And the universe answered. The atom. The smallest unit of an element that retains the chemical properties of that element. The word means indivisible in Greek. The atom is not indivisible. It is made of electrons and a nucleus. The nucleus is made of protons and neutrons. Protons and neutrons are made of quarks. Quarks are excitations of quantum fields, and the fields permeate all of space, filling what appears to be empty with the constant quantum jitter of the vacuum. From this extraordinary architecture of fields and worship particles and quantum mechanical rules, the universe has assembled itself, hydrogen burning in the first stars, heavier elements forged in stellar cores, planets condensing from stellar debris, chemistry arising from electron orbital interactions, biology arising from chemistry, minds arising from biology, and minds, eventually, curious enough to ask what everything is made of, finding the answer and being astonished by it. The atom is the bridge between the quantum world and the human world, between the physics of the very small and the experience of the very large, between the almost nothing and the everything. You cross that bridge tonight. What you now know about the atom is what took humanity 2,500 years to discover. What took Democritus and Dalton and Thomson and Rutherford and Bohr and Heisenberg and Schrödinger and Pauli and Dirac and Gell-Mann and thousands of others, working across generations, building on each other, arguing with each other, being wrong and being corrected and being right and being astonished. What took the construction of instruments of extraordinary precision and the development of mathematics of extraordinary power? What took ultimately everything that human science has produced in the service of a single question? What is matter made of? The atom. Almost nothing, almost entirely energy. Quantum mechanical from top to bottom, and out of it, everything. Good night.